Okay, so gentlemen, today we're going to learn the last two of the gas laws that we will learn. So we will have a total of seven: Boyle, Charles, Gay-Lussac's combined, ideal. And today we will learn Dalton's law, which will be the easiest of all the laws, mathematically at least, and Graham's law, which will be the most difficult, mathematically speaking. Neither of them are that bad. And remember, you always can use a calculator, but we will be dealing with square roots, so you will have to deal with that. So first, I want to talk about Dalton's law. So gas mixtures don't act differently, at least physically, than individual pure gases, as far as how they respond to pressure, volume, temperature, and number of moles. And the reason for that is because all the particles compensate at a certain temperature with their speed. Small particles go faster, big particles go slower. So when they hit the side of the container, each particle exerts the same amount of pressure. With a small particle going faster, it exerts the same amount of force as a big particle going slower. Because of that, because each particle exerts the same amount of pressure in a gas at any given temperature, the total pressure of a gas equals the sum of what are called the partial pressures from each gas. So in a mixture, each gas gives off a certain pressure. So in the atmosphere, it's about 70% nitrogen and 20% oxygen. So of our total pressure, atmospheric pressures, which is 101.3 kilopascals, about 70% of that, or about 72 kilopascals, I think, is from nitrogen. And about 20% of that, which is like 21 kilopascals, is from oxygen. So based on how much of the gas in a mixture, that's the percentage of pressure it gives off. So here I've drawn out a diagram of a standard MIG welding gas mixture. It's used to shield the weld from basically oxidation or any non-inert gases when you're welding. So the welding is actually just metal to metal. The gas provides a shield so that weld can cure properly. And a standard MIG welding shield solution, shield gas, is 75% nitrogen, 25% carbon dioxide. So in this case, I have 75% nitrogen gas, N2, with 30 molecules, and 25% or 10 molecules of CO2. They have different molar masses. Nitrogen is 28 grams per mole. The CO2 is 44 grams per mole. But that doesn't matter. Each nitrogen exerts the exact same amount of force as each carbon dioxide. Each particle exerts the exact same amount of pressure, assuming it's at the exact same temperature as any other, regardless of its particle weight. And they do that by compensating with speed. So Dalton's law simply says the total pressure of a gas mixture equals the partial pressures, which we write as P sub whatever, 1, 2, and 3, etc., of the gas mixture. We don't actually write the numbers 1, 2, 3. So for this example, P total would equal P N2 plus P CO2. So we actually write the species as the subscripted thing, and you just have as many as you have. So the partial pressure from nitrogen plus the partial pressure from carbon dioxide, shockingly, is the total pressure. So this is literally addition, and that's Dalton's law. So I'm going to talk a little bit more about it, but that's pretty much it as far as Dalton's law. Each gas particle at a given temperature exerts the same amount of pressure, regardless of its size. So when you're talking about a mixture, the particles in the mixture, regardless of their type, all exert the same pressure. So just by how many particles there are of nitrogen versus CO2, that's the partial pressures. And all you do is add those partial pressures up to get the total pressure. You don't have to compensate for the size of the particle because the particles are automatically doing that with speed. That's what temperature is, which we'll talk about a little bit more in a second. So let's say I have my MIG welding gas, and it is 75% N2 and 25% CO2, and it's at 650 psi. Actually, let's make that 650. I won't use psi. We didn't talk about that as a pressure. So 650 kPa. PSI is a standard of pressure, but it's pounds of force per square inch. So it uses pounds and inches and square inches, and it's terrible because it's just hard to do any math with that, because a square inch goes, 144 square inches per square foot per square yard. It's a whole mess. It's just a mess. So we don't have to talk about PSI. The English system, or the American standard system, is not great. So 650 kilopascals, which is about 6 atmospheres, 6 times standard atmosphere. So let's say that's at 650 kilopascals. We can tell exactly how much of that pressure comes from each gas if we know the mixture. We know that it's 75% N2, so 75% of the total pressure comes from N2. And in this case, that would be, and again, we just do 0.75 times the total, 650, equals 487.5, and that's kPa. And that's just the partial pressure of nitrogen gas. So the pressure of just the nitrogen in there is 487.5 kPa. And of course, then 650 times 0.25. So the PCO2, 650 times 0.25, equals the remaining 162. That's a terrible 6. 0.5 kPa. So I know I'm getting 487.5 kilopascals of pressure from nitrogen, and 162.5 kilopascals of pressure from the CO2. And you might think, well, that's kind of, when would we ever use this? When is this important? Well, it's actually super important for our lungs. So the pressure of oxygen in the air is what determines how well our lungs take up oxygen and when they give it off. Our hemoglobin, or the heme group on the hemoglobin specifically, is designed to take up oxygen at a certain partial pressure, around 20, and to let it off at lower partial pressures. So that means if you have a gas mixture, even if the total pressure is atmospheric pressure, let's say instead of 20%, now we only have 10% oxygen, your body is going to have a harder time getting oxygen into the lungs, into the bloodstream, and out to your various cells and systems. So it's really important for things like that. That's also why at like the top of Mount Everest, where the total pressure is about 70% of standard atmospheric pressure at sea level, you need to bring extra breathing gas usually, because since the pressure is lower, the total pressure, the mixture is the same, but the total pressure is lower. So now, instead of about 20 kilopascals of oxygen pressure, you're getting, I don't know, 70% of that's like 14 kilopascals of pressure from oxygen. And so again, your lungs have trouble taking that up, and you can't get as much oxygen to your body. And when you're climbing, particularly, I would think you'd need oxygen. You need oxygen generally, but you go through it a lot more when doing complex activity. So that's Dalton's law. And again, very simple. It's written out as, again, the total pressure here equals the partial pressures, the sum of the partial pressures. P1 plus P2 plus P3, all the way out. And when we actually write it, we replace the subscripted numbers with the actual species we're talking about. So this works if you have a mixture of 2 gases or 5 gases or 8 million gases, although that would be a pain. Just sum the totals. Sum the partial pressures. So why does that work? And this is kind of a key takeaway I want you to have from this this lesson as far as how gases behave in mixtures. Heavy particles are slower than lighter particles at the same temperature. When you did that gas laws lab, you probably noticed that the slower particles were going faster, or the lighter particles were going faster. Excuse me. That is because the lighter particles are hitting the sides just as hard as the heavy particles. That's why 100 light particles and 100 heavy particles have the same pressure. Each individual particle is hitting with the same force. The lighter one's going faster, and the smaller one's going slower. Again, you can exert the same force with a bowling ball as you can with a golf ball. However, the golf ball is going to have to be going a lot faster. Another way to think of this, if you want to hurt someone the same exact amount with a bowling ball or a golf ball, and you're going to drop it on their head, you're going to have to take the golf ball up a lot higher and drop it from a lot higher distance and land it on someone's head than a bowling ball, because the bowling ball has more mass. So it will release more energy. So temperature of a gas doesn't really measure particle speed. We talk about it like it does, and it's certainly directly related to particle speed, but it's not actually measuring that. It's measuring the kinetic energy of the particles. And those of you who have had some basic physical science, maybe in grade school, particularly if you went to a public grade school, might have learned the basic equation for kinetic energy. And you'll get this next year in physics or honors physics, or, well, whenever you take physics. But it's Ke equals 1/2 mass times velocity squared. So Ke equals 1/2 mv squared. So the mass and the velocity both matter. Now, what that means is that we can figure out the relative velocity something would have to be going to match the total kinetic energy of something else. So if we have two gases of different masses, and we know one is going 10 kilometers per hour or 10 meters per second or whatever, we can figure out what the other one is going at the same temperature, because they have to have the same kinetic energy. And the way we do that actually is the next law. It's called Graham's law, and it's Graham's law of effusion and diffusion. And we'll talk about what effusion and diffusion are. Actually, I'll do that right now. So first of all, not that one. Graham's law deals with how gases effuse, not technically how fast they're going. It's directly related to that, but measuring the speed of a gas is hard because gases spread out in all directions, and their movement is, remember, rapid, random, and constant. Well, when your movement is random, it gets really hard to accurately measure speed. So we use effusion kind of as a stand-in for speed, and in the vast majority of situations, it's kind of close enough. It's one of these things like the ideal gas law, where it's 99.9% correct in most situations, so we don't have to do the much more complex math. So, first of all, if you open something that smells, like perfume or cologne, in one part of a room, eventually, someone in a different part of the room will be able to smell that. And the reason for that is that something like cologne or perfume is designed to evaporate quickly. That's why they tend to be alcohol-based. They evaporate, turn into gas, and they carry with them certain molecules that have smell. When we smell, that is actually our nose taking up certain molecules and sensing them. Our sense of smell is actually chemoreception, chemical reception, as is our sense of taste. So you can't taste something without it physically being on your tongue. You can't smell something without it physically being in your nose, which gets really weird and gross when you think about like porta potties and farts and stuff. But that's how it works. And those things are safe, just kind of gross. So gases diffuse. That was one of the properties of gases. Basically, diffusion is the tendency of molecules to always go towards an area of lower concentration or lower partial pressure until they spread out evenly. So what you have with something like the perfume is it's at a high concentration right where it's evaporating at the perfume bottle or the person it's on, so it'll travel away from that. And it'll keep traveling away from that until the whole room is even in perfume smell, if it's possible. There's probably not enough perfume on a person to make the whole room even at an amount you can still smell, but it'll keep going until it evens out. And that's what Graham's law, or that's what diffusion basically is. And Graham's law deals with effusion, which is related to diffusion. So here is an idea of this is how diffusion works. We got a cylinder, and it has air and bromine vapor. Bromine is a gas at room temperature, but just barely above room temperature, it turns into a vapor. And it's also a dark reddish brown kind of color, so it's easy to see. So if you take this, and they're separated, they're sealed together, but they're separated. If you break the seal between them, what you'll see is eventually the air will start to move down, because it's at high concentration at the top and it wants to go to the area of lower concentration and even out. And the bromine will do the opposite. It will move up. And this is, again, diffusion. The gases move through one another without hitting, and they move till they hit equal concentration in the whole container. And if you give it enough time, in this case several hours, and the reason it takes several hours is because bromine is heavy, the bromine will actually reach the top of the column, and it will be even throughout. The bromine and the air are both spread evenly throughout that, and so that's where diffusion, it kind of keeps going technically, but it doesn't change anything. Like, it goes evenly in all directions. So you got kind of a homeostasis of pressure. That's really hard to measure. The speed at which something diffuses is super hard to measure because it happens in every direction. You'd have to find a way to set up sensors in all directions and hope that they go kind of evenly in one way or another way. Because again, it's random. That doesn't mean it's going to spread out evenly exactly. That means on average it'll spread out evenly. But at any given instant, it could be more going towards, let's say, one side of the room or another side. Random is random. So what we tend to work with when we try to measure how fast gases are moving is not diffusion, but effusion. Effusion is going out through a tiny hole in a container. In other words, you're controlling where the gas can go. And it works the same way as diffusion, though it'll actually, the gas will escape until it is even with whatever's around it. But because we are measuring from one tiny hole, we can measure exactly how fast the gas leaves that hole. So Graham's law is technically Graham's law of effusion, and it can be applied to diffusion, and less accurately, but still pretty accurately, to speed, to how fast particles are going. Because these things relate directly to speed. The faster the particles are going, the faster they'll effuse or diffuse. Because for diffusion, for instance, the faster they're going, the faster they can spread out through a room. And for effusion, the faster they're going, when they're bouncing around in a container, if they're going faster, they're more likely to find the hole and escape from the hole in the container, as opposed to something going slower. So, gases of a lower molar mass diffuse and effuse faster than gases of a higher molar mass. In other words, small things go fast and big things or heavy things go slow because they have the same kinetic energy at the same temperature. So the mathematical relation to that comes back to this Ke equals 1/2 mv squared. Kinetic energy equals 1/2 mass times velocity for a given object. So if we do some derivation, which I know you guys love, the kinetic energy of two gases equals 1/2 m gas A v squared gas A, and that'll equal, at the same temperature, gas B, which will be 1/2 m gas B v squared gas B. So if the gases have the same kinetic energy, then their kinetic energy equations must be equal. And we can, from that, derive what we call Graham's law. So all I did is put both masses on one side and both velocities on the other side by cross-multiplying. And then, to get rid of the square, this is how Graham did it. I don't know if it's better to have the square or the square root, but to get rid of the square on this side with the velocities, we took the square roots of both sides, basically. So the thing you have to know, so Graham's law as written out is here at the bottom, the rate of gas A. So that's rate of effusion or rate of diffusion, and more or less speed. We can count speed as a rate there. It's less accurate with speed, but barely and within reason for most situations. So the rate of gas A over the rate of gas B equals the square root of the mass of gas A, or the mass of gas B, excuse me, over the mass of gas A. One thing to be careful about, it's the square roots of the inverse. So it's A over B on the rate side, and then B over A on the mass side. So make sure to remember to invert those. So if we know 3 of these things, we can figure out the 4th. And generally speaking, we tend to know the masses of gases. We can figure out the molar mass of, say, carbon dioxide or nitrogen. I figured out that one was 28, N2 is, nitrogen is 28, and CO2 is 44. So if I knew how fast one of them was going, I could figure out how fast the other one was going. by plugging all those numbers into this equation. It's not the most fun equation, but again, you get to use a calculator, so not a big deal. So that's Graham's law. And you'll be working on some problems, and I'm going to go over 2 Graham's law problems examples, and that'll be the end of this video. So it takes 354 seconds for 1 milliliter of xenon gas to effuse through a small hole. Under the same conditions, how long will it take for 1 milliliter of nitrogen to effuse? So this is a rate, 1 milliliter per 354 seconds equals the rate of xenon. Well, it's not a fun rate, but it's a rate. So what we're looking for then is how long will it take 1 milliliter of nitrogen. We're looking for a rate of N2. And again, remember nitrogen gas is N2. So first of all, I'm going to set up the equation and kind of show you how to do it and work through. But I'm going to do that off screen just because it's a pain, and you don't need to watch me write about it. Okay, so I've written out Graham's law here. Rate A over rate B equals the molar mass of B over the molar mass of A. And I've also looked up the molar masses of xenon. I don't know xenon off the top of my head. Maybe you guys do. It's 131.29 grams per mole. And nitrogen is 28.02 grams per mole. And right there, we should have some clue as to how this is going to go. If the heavy one takes 354 seconds for 1 milliliter, we would expect the lighter one to go faster. So you'd expect it to be less than 354 seconds. Now, it can be kind of hard to tell exactly how much less until you do the math, but you should know that going in. We should just be able to quickly check our answer, make sure, yeah, the rate of nitrogen will be faster. In other words, it will take less seconds for 1 milliliter. So that is something to keep in mind. So I'm going to set up this problem and come back and then talk about it a bit and solve it. Okay, so I've plugged in the numbers to our Graham's law equation. Rate A for xenon was 1 milliliter over 354 seconds. I like to put xenon in parentheses here just to kind of keep my gases straight so I don't accidentally flip them. You don't have to do that. That's not necessary. I just like to. And then 1 milliliter over X seconds. We don't know how many seconds it's going to take. We know it's going to be 1 milliliter for N2. So we're looking for this X. We're looking for how many seconds it's going to take. So it's in the denominator of the denominator, which is kind of a pain, but you know, it's basic algebra, so we'll go through and solve this. And that equals the molar mass of the square root of the molar mass of nitrogen divided by the molar mass of xenon. So the first thing I did was just get rid of the square root. You can solve for this number, just plug it into the calculator and solve for it, and you get 0.46. So the square root of 28.02 divided by 131.29 is 0.46. So all I did was solve for it and then set the rates equal to 0.46. So 1 milliliter over 354 equals, divided by 1 milliliter over X equals 0.46. And then I started to get X by itself. So X is in the bottom, well, the fraction with X in it is in the bottom of our fraction. I don't like that, so I'm going to get it out of there by multiplying both sides by 1 milliliter divided by X seconds. So all I end up with here is 1 milliliter over 354 equals 0.46 times 1 over X. And then X in the bottom, but this is an equation, so I can just flip both sides of the equation and end up with 354 over 1 equals X over 0.46. And that, there in purple, is pretty easy to solve. It's kind of a pain to get to, but again, it's not beyond your abilities. It's algebra. It's not even really hard algebra. It's just muddling through rearranging equations. And you get X equals 163. But you have to remember what the question asks, because if you just got X and said X equals 163, you wouldn't get complete credit. The question asks, how long will it take for 1 milliliter of nitrogen to effuse? So you have to say, you could just say 163 seconds. That would be acceptable. Or I like to actually write out rate N2, so the rate of it is 1 milliliter per 163 seconds. But you can't just say 163 and call it a day. You have to have a unit. Or if it asked you the rate, instead of just how long, you would actually have to say 1 milliliter per 163 seconds. So that's a Graham's law equation. That's actually harder than a lot of the ones you'll get. I like to go through a slightly harder one first, because if you can follow this, you're fine. And really, the hard part is the just algebra here. Like knowing this equation and then plugging in the numbers, that's not too bad. Then it's just a matter of, oh crap, my unknown is in the bottom of a fraction, and then you have to work your way through that. But if I can do it, believe me, you can do it. So that's one example. I'm going to do one other example where instead of solving for rate or speed or velocity or whatever, we're going to solve for molar mass. So we're solving for something under the square root, which can seem a little daunting at first, but is not. So that is this question. And again, it looks complicated. It's not necessarily, so try to follow along and hopefully you'll be okay. So we've got 8.278 times 10 to the negative fourth moles of an unidentified gas that fuses through a tiny hole in 86.9 seconds. So that's a rate, moles per second. So I'm just going to write that. The rate of, I'm going to call it gas X because that's still legitimate. It's not a, you can still use X because it doesn't represent an element, equals 8.2, excuse me, 78 times 10 to the negative fourth moles per 86.9 seconds. It's an ugly rate, but it is nonetheless a rate. So under identical conditions, 1.740 times 10 to the negative fourth moles of argon gas take 81.3 seconds to fuse. So the rate of argon under the same conditions is 1.740 times 10 to the negative fourth moles per 81.3 seconds. So we've got two rates, and we can look up the molar mass for argon. So we have three of the four unknowns in Graham's law. Remember, oops, not spelled like that. By the way, Graham's law is spelled like graham crackers, so Graham. Please try to spell it that way. So Graham's law tells us that rate A over rate B equals the square root of the inverted molar masses. Molar mass B over molar mass A. So, since you get to assign what is gas A and what is gas B, you can actually make sure that your unknown ends up in the top of the numerator of the fraction on that side, which will make your life slightly easier. At least it makes my life slightly easier. It's fine to do it the other way with putting it in the denominator. But I'm going to call, in this case, since we're looking for a molar mass, I'm going to call gas unknown, the unknown X, gas B, and I'm going to call argon gas A, because then I'll be solving for something on top. And that's just, it's easier, you know, one less step. So I'm going to plug in the numbers to the equation and solve it. So I'll be right back once that. Okay, so I have gone ahead and plugged in all the numbers to Graham's law, so that those two ugly rates, argon, I did argon for A and my unknown for B, and that's just so that my unknown will be on the top of the fraction on the other side, because that's what I'm solving for. So plug those in, and then equals our unknown molar mass, X, over 39.95 grams per mole, which is just the molar mass of argon. And then the first thing I did is I just took all of this. This is you can solve this for a number, all these terrible rates, divide one terrible rate divided by another terrible rate. Turns out those equal 0.225. You plug that all into a calculator, get 0.225. And so 0.225 equals the square root of X, the square root of X divided by 39.95. So I have a square root there, and I don't want to have my x, my unknown, under a square root. That's a pain. And to get rid of a square root, all you do is square both sides. So that's why these two yellow 2's are here. I squared both sides, and if you do that, you get 0.0506 equals x over 39.95. So the square root of a square, or the square of a square root, excuse me, just remove the square root sign. So when I do that, multiply both sides by 39.95, I assume at this point you guys can solve it, I get that my x, my molar mass, would be 2.02 grams per mole. And that's likely H2. I put that. It doesn't say you have to find what it likely is, just what is the molar mass of the unidentified substance in grams per mole. It's 2.02. But the only gas light enough to be that is, H2. So I said it's likely H2. So this is one of those things where we can actually find out. It's one way to figure out what an unknown gas is. Because something like H2 isn't terribly easy to identify without doing a bunch of chemistry with it. If you want to not use any sample and just do physical tests, remember we're talking about physical versus chemical properties. If you just want to do physical tests where you're not going to use any of it up, this is a physical test you can do to find out, hey, that's likely going to be hydrogen gas. So that's one way to get around having to actually do like chemical tests on it and use some of the sample. So those are Dalton's and Graham's law. And now you have 7 gas laws that you know. So in addition to the 5 you had learned, now you know Dalton's, which is really easy, and Graham's, which is slightly more complex. So you will have a worksheet on that, and you will have a quiz this week on Wednesday on all 7 gas laws. So it'll be a 10-point quiz. It'll probably just be 7 questions, 1 for each gas law. Some of them will be 1 point, some of them will be 2. And that'll be out at 10 a.m., due at 8 p.m., same sort of thing. So after that, though, have a good Easter break. There'll be a couple more videos. I will put up a key tomorrow. I'll do a work through and a full key of the worksheet. The worksheet for this is due tomorrow night, though. It's not terribly long, but we have a shortened week, and I want to make sure you have a chance to do it and go through the key. So I'll put the key up either Tuesday morning or maybe Monday night. So, okay. So enjoy your week. Hopefully we get through this and you can get to break without too much incident.